Okay, so let's get started. Hopefully. All right. So in the previous lecture, we spoke about linear momentum, collisions, conservation of linear momentum in 1 dimension and 2 dimensions. I've sent an updated course plan by email to everyone, and also uploaded it on Moodle, reflecting the lectures that were cancelled because of national holidays, the problems we have faced with quizzes, some changes. I hope everyone takes a look at that. A side effect, good or bad, depending on your point of view, is that we are removing 1 chapter for the time being from this course, which is chapter 15, oscillations. Now, I am particularly unhappy about this because oscillations are a really interesting topic, which actually has a lot of practical implications, but there's really nothing we can do. We have lost 3 to 4 lectures, which amounts to almost 2 full chapters or 1.5 chapters throughout this semester. Nevertheless, I've also updated the quizzes, how it's going to work. So all the details you can find there. It's already in your email inbox and on Moodle. Okay, now, today we are starting lecture 21, chapter 10. Noor, hopefully, we're starting lecture 10, chapter 10 today. And chapters 12 and 13 are only half chapters covered, as if you look at the course plan, we're only doing half of each chapter. Okay, so we're not covering the full material as we would like to, but at least to give you some exposure to the material. So hopefully, if we don't finish, then, well, we don't examine. It's that way. Okay. All right. So let's start. I shall share my screen. No, chapter 11 is still there. Chapter 15 is the one that was removed, Mariam. Okay. So at the very beginning of this course, we had spoken. Chapter 14 was never part of the course, actually, Wad. Yeah. So, Ahmed, I did not forget, I have a problem because the textbook file I have is about 300 MBs and I am unable to put it on Moodle. So I'm compressing it and it should go on, hopefully, by, well, hopefully before the end of our lecture, it should be live there. Okay? All right. So at the beginning of this course, we said that there are 2 types of motion, translational and rotational. And we gave a couple of examples on each. Now, everything we have done so far has been on translational motion. Okay. Today, we are actually going to work with rotational motion. And, well, hopefully, start looking at a different sort of type of physics. Now, a lot of what we're going to be doing today is going to feel like a repetition, okay, of what we have been doing so far, okay, only in a different setting. So I might eventually start going a bit fast, and if you have a problem with that, just, you know, let me know and tell me to slow down. Okay, fixed axis rotation. Let's start with what we call rotational variables. Let's just imagine a random body, like an egg, for example, so it's not uniform in all directions, and rotate it. The first thing you will notice if you try to rotate something is that you need to decide about what axis you need to rotate it. So if I'm looking at this calculator, it's very different if I rotate it above the center, and this is too big for my hand to be able to do comfortably. So let me try this better. Okay, if I choose about the center, it rotates this way. Okay, now if I hold it about this way, it will still rotate, but the rotation will be different. Okay, there are some things that are different, whether I fix it in the middle or fix it on the side or fix it somewhere else. Okay, so this is what we call the rotation axis. Okay, here my rotation axis is the y-axis. Now my rotation axis is the x-axis when I'm doing this. Okay, and we identify what we call something a reference line, which is a part of a body which is perpendicular to the rotation axis. So if I have this pen, my rotation axis is this, the pencil. This will be my reference line. Now, when something is rotating, it's moving. Okay, let's take a look at this reference line. Okay, and it's in purple here, and see how it moves. If we just take a look at that one reference line, we will look at it, and it will move. Okay, it's the same as looking at a fan, just focusing on one of the arms and looking at it move in circles. Okay. Now, how do we describe this movement and these locations? Okay. So similar to linear motion, where we have x1 and x2, okay, for positions, here we have theta1 and theta2, where this is theta1, this is theta2. Okay, so because you're going in a circle, your distance is no longer, or your movement is no longer measured in x1, x2 in meters per se, but in angles. Okay, and of course, we're going to see later on, we can convert between x and theta and vice versa. So first thing first, x and theta. Now, if we take something and we rotate it counterclockwise by an angle theta, we call that the positive direction. We call counterclockwise positive and clockwise is negative. Can we do it the other way around? It is possible, yes. Okay. But the general direction is usually counterclockwise positive. And personally, I tend to remember that as no one wants to get really old. So going against the clock, getting younger is a good idea. It's positive. Going with the clock means you're getting older, and that is bad, negative. Okay. So the reminder, this direction is positive. This direction is negative. Now, our angular position, theta, here, can be found by looking at how much in meters did the reference line move divided by the radius you have taken to the S line. Okay, so this is my reference line. This is R. This is S. My theta here is going to be S over R. If I take the rotation about the same place, but I decide to instead measure my S this way, further off. Oops, nope, this is not supposed to be this. Yep. Okay. My theta is still the same, but my S is bigger and my R is bigger. Yes, it's an arc. Yes. So the theta you end up is still the same. whether you go for S black over R black, over S blue over R blue. Okay. Now, what is the units of this thing? Now, theta, we are used to giving angles in degrees. Okay, but degrees isn't actually its, let's say, strictly proper unit. The proper unit strictly is called radians. Okay, radian. And so we will measure theta in radian. If I go one full circle, one revolution, that is 360 degrees. And as you remember from trigonometry, that is equal to 2 pi in radians. And if I look at the full distance I have moved, it will be 2 pi r. So if I look at my theta, it's going to be 2 pi radians. This is how we define the full circle to be 2 pi radians in theta. 1 radian is approximately 57.3 degrees. So usually we deal with things that are smaller than full radians. Now let's look at circumference. So your circumference would be 2 pi r. Yeah, your full circumference would go through 360 degrees. Okay. Now, let's go to angular displacement. We already did normal displacement, translational. Okay. Now we have angular displacement. If I go from theta 1 to theta 2, then my displacement is delta theta, theta 2 minus theta 1. Very simple. Just like we had delta x equals x2 minus x1. Counterclockwise is positive. Clockwise is negative. So far, so good. Any confusions? We haven't done any mathematics so far. We have just been defining things. We have worked on the definition of theta and delta theta so far. Yes, Rayan? Not when we're looking at rotational motion. In rotational motion, usually what we do is counterclockwise is positive, clockwise is negative. Yes, مع عقارب الساعة clockwise, عكس عقارب الساعة counterclockwise. But for some reason, someone many years ago decided that, you know what, I'm going to be funny and do it the other way around. X is translational displacement, going from point 1 to point 2. I am here, and I end up going here, then this is x2, and this is x1. So this is the x that we have been dealing with since the normal distance that we have been dealing with since chapter 1, before dealing with angles. Okay, we looked at angular displacement. Next, naturally, just like we did displacement and then velocity in translational, we do it in this. No, ما من الرسمة. So what we're going to be doing is we're going to be defining each one of the quantities that we have done before again. So let's look at angular velocity. What is our average angular velocity? Any ideas? No. What was our normal average velocity? Okay, W. Yep. So our normal average velocity was V2 minus V1 divided by 2. Or, more generally speaking, delta V over delta T. Delta X over delta T, correct? Displacement over time. Well, here we do the exact same thing. Angular velocity is angular displacement over time. Delta theta over delta T, and we use omega. So you will notice something over and over again, okay? For translational variables, we use what we call the Latin alphabet. A, B, C, D, E, F, G, and so on and so forth. This is for translational. For rotational, so as to avoid confusion, what we do is we use their Greek alphabet analogs. So you would know these as alpha, beta, delta, epsilon, mu. Okay, I'm not, so alpha is A, beta is B, delta is D. I don't know what the rest is. Okay, so V becomes omega. Theta is in radians, time is in seconds. So your angular velocity instead of meters per second, it's now radians per second. Or another way to look at it is revolutions per second. How many circles do I go in 1 second? Okay, if you are into cars, you would notice that, or if you just drive a car, you would notice that you have a, right next to the speedometer which tells you the speed, you have another one which tells you the RPM, revolutions per minute for the engine. Okay. What is our instantaneous angular velocity if our average angular velocity is delta theta over delta t? I mean, it's going to be the limit of delta theta of delta t as t goes to 0. So it would be the derivative, d theta by dt. So our v was dx by dt. Here we have d theta by dt. Let's take a tiny look. The diameter of the sun is 400 times that of the moon. By coincidence, the sun is also about 400 times further from the Earth than the moon is. For an observer on Earth, compare the angle subtended by the sun, so theta sun, and the moon, theta moon, as shown in the figure below. So what do you think it's going to be? A, B, or C? Much larger, much smaller, about the same. Couple of A's, couple of B's, a few C's. Okay, so an even spread with most people saying C. Here's our calculation. Just a second. Here's the calculation. When trying to calculate theta, we said theta equals S over R. Theta moon equals S moon over R moon. Theta sun equals S sun over R sun, which happens to be 400 S moon over 400 R moon. .400 over 400 cancels out. We end up theta sun is the same as theta moon, which is why we have the eclipse. Because although one is way larger than the other, it's also way further away than the other. So it appears to us as if one, so the angle subtended is the same, so it can cover the light coming from this. Okay, average angular acceleration. By now, you have gotten the gist of how this works. Okay. Omega 2 minus omega 1 over T2 minus T1, delta omega over delta T, and d omega by dt, given by alpha instead of A. Where is the radian different, Mariam? How is it different? We just did the calculation here, and the radians are both SM over RM. So they're both the same. Look at the numbers and tell me where did I go wrong. So for the moon, we simply have S moon over R moon. For the sun, we have S sun over R sun. There's a fixed relationship between them. So S sun is 400 S moon. So I substitute that. Coincidentally, also, R sun is 400 R moon. Now the 400s cancel out, and I end up with just SM over RM. So these two are exactly equal. Question? No? Okay. I have somehow. Okay. All right. So acceleration will be in radians per second square or revolution per second square. Let's look at a problem. If the angular acceleration of a spin top is alpha equals 5t cubed minus 4t, with t in seconds and alpha in radians per second square, at t equals 0, the top has angular velocity of 5 radians per second. And the reference line on its angular position theta equals 2 radians. Obtain an expression for the angular velocity. What's omega going to be? How do I convert from alpha to omega?
Doctor, I think to integrate this equation.
Good. Excellent. So if we want to go this way, we derive. If we want to go reverse, we have to integrate. We integrate, and we get 5 over 4 t to the power 4 and minus 4 over 2 t squared plus c. Are we done though? Not yet. Because the question actually gave us an extra piece of information. It told us that at t equals 0, velocity is 5 radians per second. We substitute that and we get c equals 5. So our omega is actually 5 over 4 t to the 4 minus 2t squared plus 5. Excellent. Obtain an expression for the angular position. Again, we integrate. This is our speed. We integrate again. And we will end up with 5 t to the 5, 4 times 5, minus 2t cubed over 3 plus 5t. The 5 and 5 are going to go away. You're going to end up with t to the 5 over 4 minus 2t cubed over 3 plus 5t. Do you have any extra information that we can use? No, so it's just going to remain at plus c. We don't know what the plus c is. Okay. Now here's a question. Every time we spoke about velocity of our acceleration or displacement in translational variables, we kept going on and on and on and on and on about vectors. So are angular quantities also vectors? Okay. Yes. No. What do you think? Yes. So the right-hand rule comes to the rescue again. Remember we did the cross product with it? 1 A, B, C, back in vectors. Well, we have another right-hand rule now to establish the direction of the angular velocity vector. Okay. Now, angular velocity are a bit weird. Okay. So you look at the direction of rotation and you have your fingers curl along with them. So if your rotation is going this way, your fingers curl along with them this way. If your rotation is going that way, your fingers curl with them that way. The direction of your thumb tells you the direction of your angular velocity. Have you ever taken a CD and started spinning it around and noticed that it's going up with time or down with time? This is the reason. Your angular velocity is actually perpendicular, right hand. Okay. Omega and alpha follow vector addition. So just like what we have been doing so far. Let's look at an example. An electric clock hanging on a wall. As you are watching the second hand rotate, the clock's battery stops and the second hand comes to a stop over a brief period of time. So very short period of time. Which one of the following statements correctly describes the angular velocity and angular acceleration of the second hand as it slows down? Angular velocity and angular acceleration are both negative. Angular velocity is positive and angular acceleration is negative. Angular velocity is negative and angular acceleration is positive. Angular velocity and angular acceleration are both positive. Okay, couple of D's, couple of B's, a C or a B. Now remember, this is a clock, which means the second hand is moving clockwise, which means its omega is clockwise. And what did we say clockwise is? We said that, I don't find, here we go. We said that clockwise is negative. My omega is going to be negative. Now, because it stops, it means it accelerates in the opposite direction, which means alpha is positive. So the correct answer is C. So we have spoken about angular velocity and angular acceleration, and we said they are vectors, but we did not actually speak about displacements. Now there's something weird about angular displacement. Now usually I demonstrate this in the lecture theater. Unfortunately, we are not in lecture theater. So this is the best I can do. But if you have a book beside you, okay, or anything that looks like a rectangle, bring it. Why? Because it's in the opposite direction to velocity. If you are going this way and you stop, it means your acceleration was in the opposite direction. Okay, if you have a book or something rectangular, bring it close by and we'll try to do it together. Give you a few seconds. And I am going to be using, nope, a music calculator. Okay. Okay. Let's try with this box. Why is this the wrong way around? Okay. It's mirror image. Okay. Here's my rectangle. I'm going to do a series of 3 movements. 1, 2, 3. Okay? I'll do it again. It was this way. Sorry, it was this way. Okay. Let me do it exactly the same. So the price thing is straight up. I will take it up. I'll bring it down. I'll take it down again. And I end up with this face. Okay? Okay. Now I'm going to do the exact same thing. Look, it's the same side up again. I'm going to do the exact same thing, but in a different order. So first, okay, instead of first going up and then down, I will first go down, then I will go up, then I will go down again. What is the problem? What just happened? Excellent. My final position is not the same as the final position in the first place. Let's do it on the screen, and then I'm going to explain it again. Here's my book. I will take it up first, and right. And here's the same book. I will take it right first, then up. And I end up with 2 different final positions. Okay. Now, this is a big problem because what is something that we have depended on our entire lives? We have, for our entire lives up until this point, we have depended on something that we have taken as a granted. That if I do A plus B plus C, or I do C plus B plus A, I will get the exact same number, right? And this is okay for vectors. Actually, to be more accurate, for something to be called a vector in the first place, this has to be true. Okay. Now, the fact that this is not true for angular displacement tells us that angular displacements, okay, are not vectors. They cannot be treated as vectors. So theta, sorry, thing, vector. Theta is not a vector. Omega is a vector. Alpha is a vector. But theta is not a vector. You cannot deal with it as vectors. Okay. Let's summarize everything we have said so far. Or before we do that, let's do something else. We had some equations in linear motion, and we had some variables in linear motion. Okay. And linear might not be the best term, so I'll call it translational motion. We had x, v, t, a, and v naught for initial velocity, or sometimes I called it u. Well, let's translate. X becomes theta, v becomes omega, t is still time, a becomes alpha, v naught or u becomes omega naught. Okay? It's like translating. When you don't understand something in Arabic, in English, you translate it to Arabic. And we are doing the same here from rotational to translation. If I forget what omega is or what do I do with it, I remember it is the brother of v. If I forget what alpha is and what to do with it, I remember it is the friend of or the brother of a. Now, what about equations? We had v equals v naught plus at, or we actually called it u plus at. In rotational motion, we translate. V becomes omega, v naught becomes omega naught, a becomes alpha, t is still t. We had s equals ut plus half at squared. What does it become? Theta equals omega naught t plus half alpha t squared. We had v squared equals u squared plus 2as. I get omega squared equals omega naught squared plus 2 alpha s. I had, for average velocity, you add up two velocities and divide by 2. For average displacement, here I do the same with velocities and then multiply them by time. I have this. And now I have this. So same equations. We don't need to remember new equations. Certainly, I have never memorized these equations in their angular format, in their rotational format. I only know v equals u plus at, s equals ut plus half at squared, and v squared equals u squared plus 2as. And I have always, even in exams when I was a student, what I did is, because, well, you get an equation sheet, I did not. So what I would do is, I would simply write this in the exam, and then literally on the paper translate it to this. Okay, so think of it as English-Arabic dictionary translation. Let's do a sample problem. The angular velocity of the cylinder decreases from 3.4 radians per second to 2 radians per second in 20 revolutions at constant angular acceleration. What is the constant angular acceleration during this decrease in angular speed? I'll give you a minute to do it, and then I will do it here. Okay, so some are saying 0.07. Some are saying minus 0.07. Rev is revolution. Okay, so most people agree with the number, but just with the sign they have an issue. Let's take a look. My change in my distance is 20 revolutions, which I can convert to 125.7 radians. How did I do that? One revolution is 2 pi's. So 20 times 2 pi equals 125.7. This one, right? Okay. Omega naught is 3.4 radians. Omega final is 2 radians per second. V equals U plus AT. Translate. Omega equals omega naught plus alpha t. Again, translate. We don't have time. We have distance. We have initial and final velocities. So personally, I think what I would use is V squared equals U squared plus 2AS. That would mean omega squared equals omega naught squared plus 2 alpha, the distance. Omega squared is 2 squared. Omega naught squared is 3.4 squared plus 2 alpha. And my distance is 125.7, which means 2 squared is 4 minus 3.4 squared minus 7.56 divided by 2 divided by 125.7. I am getting minus 0.03. Radians per second squared. Okay, so just like we did in chapters 3 and 4, only now using different letters. Okay, be careful with the whole radians and revolutions. I have chosen this sample problem for a reason. Okay, because many students don't pay attention to revolutions and radians. It's extremely important when you read a question to notice if there's a mix and match between them, or if it's only revolutions or only radians. As usual, my advice is whenever doing any problem, convert everything first to SI units and then do the problem. Yes, Mariam? Yes. So 1 revolution equals 1 round, which equals 2 pi r in distance. Okay. So if you have 1 revolution and you want to find how many thetas that is, you multiply it by 2 pi.
دكتور
Yeah.
أقصد تو إحنا لما عوضنا في ذا القانون 2 باي الآر اعتبرناها 20.
لا
ليش
الار
عوضناها
ما
ب 20؟
20. الار ما 20. كيف الار 20؟
أنا سويت ترى الآر ما 20 بس يعني لما سوينا 2 باي ضربنا في الآر عوضنا عنها ب20. كيف 20؟
ليش عوضنا الار ب 20؟ نحن ما عوضنا الار ب 20. احنا قلنا انه هذا كامل الدويره الواحده is 2 باي. 20 دويره معناتها 2 باي تايمز 20 تساوي 125.7 راديانس.
القانون ما 2 باي آر؟
لا.
أوكي تو فهمت. شكرا.
هنا عملنا القانون. okay. فلما الحين نحن قلنا 125.7 طيب معناته it went through 7,200 degrees. دويرة ورا دويرة ورا دويرة. I don't get the question, وعد. Okay. They're equivalent in the sense like saying kilometers are equivalent to meters. You cannot use kilometers when you want and meters when you want. Yeah. What you either have to have both of them in revolutions or both of them in radians. So if you don't want to make the revolutions to radians, you can keep it, but then radians per second, you need to convert it to revolutions per second. Yeah, it's like when you have 1,000 meters and your velocity is 2 kilometers per minute. You cannot multiply these two numbers together. It just doesn't work. زين مبروم على مبروم ما يرولش. العكس you divide by 2 pi. If you have 2 radians per second, you can go 2 radian divided by 2 pi 1 over second. 2 divided by 2 pi is 0.318. So you get 0.318 revolutions per second. And if you multiply that number again by 2 pi, you will get 2 radians per second. Okay, it's like converting between kilometers and meters. Exactly the same. Okay. So how do I relate linear and angular variables? What we have been doing so far is translating, saying omega is like V, theta is like S, alpha is like A. But now the question is, if I actually have A, how do I get alpha? If I actually have V, how do I get omega? Okay, not simply by translating to make the equations to make it easier for us to remember the equations, but to how to actually do the calculations. We said that A is similar to alpha, yeah? But if A is 2 meters per second squared, I cannot say that alpha is 2 radians per second squared, right? This is not correct. So how do I actually convert? Okay, what are my conversion parameters? Well, let's think of this weirdly shaped thing. So I've obviously not chosen a circle for a reason. Okay, let's look at this weirdly shaped thing, and there's a person standing on it. Now, if this person is at a distance r1, and there's another person on the same object at r2, okay, so this makes it look nicer. Now, they are going through the same 360 degrees, correct? The same 2 pi radians, the same 360 degrees, same 1 revolution. Do we agree so far? But there's one problem. Look at the path they actually take. Something's very weird is going on. It seems that the person who is on the outside moves a much larger distance in terms of circumference than the person who is on the same object going through the same 360 degrees in angles through the same 1 revolution. The blue path is much smaller than the green path. So if I am, and remember, they are going through the same circle in the same time because they are on the same object. Now, if my velocity is equal to distance over time, how do I compare the velocities of the guy in orange and the guy in black? They have the same omega, they have the same t, they have the same 2 pi, yet when I look at V1 and V2, V1 is way more than V2. Yeah, they're way more than V1 than V2. If I just take the circumference, 2 pi r, one r is way bigger than the other r, so it would appear the orange guy is going at a much higher velocity than the guy in black. That's weird. Look at this. Look at it carefully. Look at the red dot alone, and then look at the blue dot alone, and tell me what you see. Bear in mind, they are on the same stick, and they are going through the same circle in the same time. Good. Excellent, Ahmed. Blue seems to be slow, and red seems to be fast. Because in the same time, red is going through the big circle, while blue is going through the smaller circle. Okay. So our position, we had defined theta equals S over R. So S equals theta R. Our velocity is ds by dt. And we end up V equals omega R. And acceleration is d omega by dt. So we end up with at equals alpha r. So to get the translational variable, we take whatever the angular variable is, and we multiply it by r. And we get something nice out of it. We get something called T, capital T, T 2 pi over omega. This is how long it takes to go one circle. How many seconds it takes to go in one circle. So it is possible, what we learn from this is, it is possible for two objects to be on the same rotating body and yet have two very different velocities, translational velocities. Two objects can have the same angular velocity, but different translation velocities. Okay, which part? Okay, let's start over. In the beginning, when we defined the line of reference, we said theta is equal to S over R. So far, so good? Where S is the translational variable, the straight distance, if you wish. Do we agree on that so far? Okay. Now I will just simply rearrange this to say S equals theta R. I just took the R up. So if I have theta, my angular variable, I multiply it with the radius, and I get the translational variable. So far, so good? You can think of it as this, X. Okay. Now, if I want speed, how do I get speed from position? I take the derivative, right? ds by dt, or dx by dt if you want. ds by dt is d theta r by dt. Now, r is a constant. It doesn't change because it's my radius. It's just a number. I kick it out. What is d theta by dt? Omega. I differentiate this again. Ignore this bit. I'll come back to it. Okay, I differentiate it again, and I get A equals alpha r. And this A has a T here because it's what we call tangential acceleration. And I'll explain what this is in a second. Now the question is, what is this bit? Well, time equals distance over velocity, correct? If something is going in a circle, what is the total distance it goes in one circle? We will come to this, Mariam, in a second. Yeah, time equals distance over velocity. My total distance in one circle is 2 pi r for the circumference divided by v. What is r over v? R over v is 1 over omega. So I can simply replace this with 2 pi over omega. It gives me what we call a time period. How long does it take for an object which is here to go one full circle? Now, previously here, I said there's a t here, and I'll come back to it. Now, what kind of acceleration is this? It's a tangential acceleration. It's what an object here at the edge would feel its acceleration is here, tangential. Okay. But we can also write this in terms of angular velocity. Yeah. So Mariam, you said A equals V squared over R, which we already know, correct? So if we say A equals, yes, exactly, not like circular motion, circular motion. We are going in circles now, right? Circular motion. So we know A equals V squared over R, and that is the same as saying omega squared R. Okay. Let's do a numerical problem to make this a bit clearer. A few more minutes and a few more slides. Good. We are given a job of designing a large horizontal ring that will rotate around a vertical axis that will have a radius of r equals 33.1 meters, matching that of Beijing, the Great Observation Wheel. Okay. Passengers will enter through a door in the outer wall of the ring and then stand next to that wall. So this is one of those playground games where you have a circle and everyone stands here. You are usually strapped in, hopefully, by some belt. And then they close the door and then this thing goes in circles very, very quickly. Okay. So we have radius r equals 33.1 meters. Passengers will enter through the door, stand next to the wall. We decide that for a time interval from t equals 0, from the moment you switch it on, to 2.3 seconds, the angular position of a reference line will be given by theta equals ct cubed. C is some constant. And after 2.3 seconds, the angular speed will remain constant until the end of the ride. Okay. Now what happens is once the ring begins to rotate, the floor of the ring will drop away. So there will be nothing holding you from beneath, but the riders will not fall. They will feel as if they are pinned to the wall. For time t equals 2.20 seconds, let's determine a rider's angular speed, linear speed, angular acceleration, tangential acceleration, radial acceleration, and full acceleration. Okay, I'm going to write all of these on a piece of paper because that's quite a few things. Okay. Let's start. Radius is 33.1 meters. We have two people on the edges. The bottom goes off. At t equals 0, we start from scratch. Omega naught equals 0 radians per second. We don't know what our acceleration is, but what we do know is that this is everything we know. We don't know what's acceleration. We know that we start from 0 radians per second. We accelerate for 2.3 seconds. And after that, we stop accelerating. And we know that the angular velocity of this person moving between 0 and 2.3 seconds is ct cubed. How do we find all of these? Omega, V, AR, AT, A. Although this seems like a really complicated problem, you will see that it's actually quite straightforward. Let's do them one by one. Omega is simply d theta by dt. Why is angular acceleration 0 after 2.3 seconds? Because that's what the question said. It said that after 2.3 seconds, angular speed will be held constant. Constant means no angular acceleration. Okay. Since we have theta, omega is simply the first derivative. D by dt of theta is 3 ct squared. We know what c is. We want to find everything at 2.2 seconds, so we substitute that in and we get a number. So that's omega. Next, v. How do I find v? Anyone? We have a ready-made equation for it. No? We convert. V equals omega r. So we take whatever omega we had, we add an r. Done. Now we want alpha. How do we find alpha? We have omega. We differentiate again. We get alpha. So the fact that they gave you what theta is made your life easier. You immediately can tell omega is 3 ct squared. Alpha is equal to 6 ct before you even do anything else. Now, what is AT? Excellent. Alpha r. So you just add an r to it. And what is angular acceleration? Sorry, AR, the radial acceleration. Yes, alpha is angular acceleration. Sorry, I made a mistake. So angular acceleration is 6 ct. Tangential acceleration is 6 ctr. Radial acceleration is omega squared r. And my total acceleration, total linear acceleration, is the modulus. Let me explain that last part of it. Now, when something is going in a circle, okay, and that something is here, that something will have what's going on? That something will have two accelerations. It will have a tangential acceleration in this direction, and it will have a radial acceleration, which is usually in this direction. Okay, sorry, that's the wrong direction. This direction. We called it this before, AC, centripetal acceleration. This. Okay. Alpha is how fast it's going in a circle. Alpha is a measure of how many degrees it goes. A is how many meters it goes. So your total acceleration, since you have two components, will be AT squared plus AR squared all square rooted, the magnitude of two vectors. Okay, two very quick things. It's going to take 1 minute and then we're done with this lecture. The Earth rotates once per day about its axis, which is perpendicular to the plane of the equator. So this is the axis of rotation. Where on the Earth's surface should you stand in order to have the smallest possible tangential speed? Excellent. V equals R omega. So to get the smallest possible V, omega is the same for everyone on Earth. Yeah. But to get the smallest V, you either need to be at the North Pole or the South Pole, where you have the smallest possible radius. Excellent. This is what it looks like. It looks as if the people on the outside are going way faster than the one on the inside. Okay. Is it possible to build a clock in which the tips of the hour hand and the second hand move with the same tangential speed, so with the same v? Is it possible or not? This is normally never done. Why? If it's not possible, then it's not possible. But, sorry, yeah. That's wrong. It's not is it, it should be it is possible. It is possible to build a clock in which the tips of the hour hand and the second hand move with the same tangential speed. Why is this normally never done? But most clocks have it the same length for all three. So if we look at the angular velocity, okay, they don't go with the same angular velocity, do they? The second hand goes 60 revolutions in 1 hour, but the hour hand goes only 1 revolution, not even 1 revolution per hour, sorry, my bad. The second hand goes 60 revolutions per hour. The hour hand goes 1 revolution per 24 hours. Which means that to have the same v, the length of the hour hand would be 720 times than the length of the second hand. It's pointless. Okay? Because if you want v equals to v with different omegas, you will need to have 60 R60 rev per 24 hours equals R1, and R2 the same as, sorry, 1 revolution per 24 hours equals to R2 60 revolutions per 1 hour. Okay, good. You are looking at the one that goes twice. Okay, so 1 revolutions per 12 hours. Let's do that. Good point. We will end up with R1 divided by R2 equals 60 times 12, which is 720 times greater. Okay. All right. So with this, we end our lecture. Sorry, I overstepped today. I took 5 extra minutes. We can stop the lecture now.